The last speaker in this morning's session is Arun. I shouldn't say his surname. And he's a professor in Eurocom currently and did his PhD in Michigan. So let's listen to him.
So I'll kind of go over a top level, give you a big description of the broad setting, then talk about the scenario I work on, and then get into the details and the new elements. So the broad setting is quantum measurement compression, and the broad question is, how much useful information does the outcome of a quantum measurement contain? So I'll just, it's a pictorial talk, so there's a lot of pictures. So and I'll also do the math at the end. So suppose I use this to kind of denote a quantum state, and this is a probe or a measurement. I have two outcomes, and when you make a measurement, as all of us know, the outcome is random. You get a post measurement state and a classical state. So the outcome could be blue or the outcome could be red, and it happens with some probability. And the question is, is this just completely random, or there is some useful information about the state in the outcome? And the question is, how much useful information is contained? So that is the broad question of interest. And this is not easy to formulate, but thanks to Winter, it was an elegant formulation in 2004 following a series of works, and a very nice solution and an elegant answer to the problem, both like intuitively and mathematically. I'll just describe that, and then I'll tell you the setting that I work on. So I consider the simulation of a separable POVM on bipartite states with components distributed at two locations. So I will explain these terms. So I have a bipartite state, distributed components, possibly entangled at two places. So I have row 1, 2, component 1 at one place, component 2 at another place. I have a POVM that whose outcome I want to understand how much information is there of the two states in the outcome. That's the broad goal of the problem. There's one error in my slides. It's so the lambda z and the lambda y are interchangeable. So if you see z, it's same as y, and if you see y, it's same as z. So I have this POVM, and I want to find how much useful information is contained in the outcome of that POVM when I perform this measurement on the bipartite state rho 1, 2. So what do I mean by a separable POVM? What I mean is that I can decompose this POVM into two POVMs, mu w1 and mu w2 for j equal to 1 to 2. And I can do some stochastic processing so that I can simulate the lambda y or the lambda z. Okay. So in other words, I can perform these POVMs at two separate places, and then I can mix the outcomes through a stochastic channel, and that will essentially simulate the lambda y or the lambda z. As I mentioned, the lambda y and the lambda z are interchangeable. So that's what I mean by a separable POVM. So in other words, I can implement this in a distributed fashion and then send the outcomes W1, W2 to somebody who can stochastically process it, and the essence is the measurement has been simulated, the lambda z has been simulated. And the question is, how much information does these outcomes W1 and W2 contain about the state rho 1? That's the broad question of interest. So I'll just tell you what is the kind of the formulation, what I solve, and what are the results, and then get into the details and tell you what is the novelty. So I study both. It's a Shannon theoretic study, as most of you might here be able to understand. It's a Shannon theoretic study, so I study both the one-shot and the asymptotic versions, and I'm able to obtain I can fit any POVM and then obtain bounds on the amount of information that comes out of that. So in other words, if your POVM requires to be, so if your lambda 1, lambda 2, or your mu 1 and mu 2, mu w1, mu w2 has to be simulated via some joint structured POVMs, I can simulate that. If it is to be done with unstructured codes, I can simulate that. All of that is possible through this setting. So that's the broad thing. This picture is a little complicated, but I will build upon it slowly. So you will see it come along. Essentially, you see the same thing here. I have a bipartite state. two separable POVMs, and I'm trying to simulate that at the end. Okay, so I will actually explain this further. So what is the specific technical contributions? Well, I've come up with a new likelihood POVM. I can analyze it in all regimes, one shot, asymptotic, and get simpler proofs, and essentially generalize it to multiple settings. That is the broad picture. So just elaborate a little bit on this before I get into the details. So you can take any measurement compression scenario if it's distributed, or one measurement on, or rather multiple measurements on a single state, or multiple distributed measurements, or with some side information. All of this can be handled in one setting with the likelihood POV. So the proofs are very simple, can work in both the one shot and the asymptotic, and then it can be extended to other problems you might be knowing of, purity distillation, or quantum reverse Shannon theorems. All of that can be done using the same framework. So I will I'll just making connections to other problems. So this quantum measurement compression is connected to soft covering, it is connected to classical covering, Wiener-Zev, and all of those problems. Even quantum communication has the aspect of covering the environment space. So you have these. So these likelihood POVMs can be used in all of those settings essentially. So let me just, some of you might not be clear with the measurement compression. So let me just formulate this problem and then come into the details of the distributed scenario. So what is the quantum measurement? What is the formulation? And how do I formulate it in the distributed setting? So let me just mention that. So you have a state, rho. You have a POVM lambda y, and the question of interest is how much information is contained in the outcome of the measurement. So how do I formulate this? It goes back to Winter's work, but I will just kind of describe this formulation. So when I make this measurement, I get a post-measurement classical quantum state, rho and outcome y, and so this is the action of the original POVM. So what I want to do is I want to simulate this post-measurement state using a different POVM, and then characterize how much information needs to be communicated to be able to extract that classical outcome. That's the question. So how do I do this? So let's take the state rho. I'm going to give C bits of shared randomness between the encoder and decoder, C bits of complete randomness, shared randomness that is independent of the state. And I'm going to give a noiseless link of rate R from the encoder who holds the state to a decoder. And suppose I can construct a new POVM mu W whose outcome has only rate R, and that rate is that the outcome W is communicated to the decoder. And with this C bits of randomness, if the decoder can actually post-process and get the Y out, then I've essentially simulated the post-measurement state using an alternate POVM. So let me explain this once again. So if I make the original POVM, I get the post-measurement classical quantum state. So the way I so the alternate approach to kind of simulate this post-measurement quantum state is you give C bits of randomness between the decoder and the encoder, and you come up with an alternate POVM mu W. That W has classical outcome of say R bits of information. You send that R bits to the decoder. Now if the decoder can use these C bits, which is completely independent of the state, and the R bits that communicated from the encoder to simulate the Y that was actually of the original state, then you have essentially simulated the POVM perfectly. And so then the information content in the outcome is just R. So that is kind of the information content in the outcome of measurement. So that is kind of the formulation. So I will just put this in. So the simulated post-measurement state, so here there's a Y at the behind the window which you're not able to see, but the simulated post-measurement state Y and the post-measurement quantum state must be identical to the. So this post-measurement state Y, classical random variable Y, and the post POVM now simulated through an alternate measurement. If it is identical to the post-measurement classical quantum state that the original POVM would have given you, then you've essentially simulated the original POV. And you're able to do that with only R bits communicated from the encoder to the decoder as against to entropy of the Y. So R is actually the information content in the outcome of the measurement. The extra C is just complete randomness that the measurement is kind of throwing out. So that is the formulation. So so I'm going to just write this in math. So essentially, I have an original POVM lambda y, and I'm going to, so the post measurement state is IX tensor E lambda on rho, phi rho, a purification of rho. Now, what I'm trying to do is I'm going to take C bits of randomness, and I'm going to choose an alternate POVM. So that's my theta. And I'm going to do some stochastic processing. And that is indexed by this K, which is a common randomness. And if I'm, if I kind of mix these different states, and if I can get to the original with an epsilon, then I've essentially simulated the state. Essentially simulated the post measurement state. And hence I only need to communicate R bits to the decoder. So R is the kind of the information contained in the outcome of the measurement, and the extra C is just completely random. That's kind of the formulation. So I will push this in the separable, in the bipartite distributed state. So I have so this is my post measurement state coming out of the original POVM. So I will try to simulate this via common randomness and rates. So I'll give two common randomness links, C1 and C2, between the encoders and the decoder. I will give rates R1 and R2 from the encoders to the decoder, and I'm going to start. I'm going to do some an alternate POVM on the two states, and try to simulate the same Z and the post measurement state through this setup. And the question is, for what rates R1, R2, C1, C2 will I be able to do that? So then R1, R2 tells me the information content of the outcome of the measurement. That's essentially the story. So so what do I need? I need at the end of the day, so I can take any POVM W1 and W2, and so long as I can ensure that the post measurement state coming out of this alternate POVM followed by classical processing at the decoder, if this is identical to this, then I've essentially simulated the POVM. And I want to just characterize the set of all R1, R2, C1, C2 pairs that can do it. And so I just formulate, it's just the extension of that with a K now becoming K1, K2, and then I have the lambda, the theta K kind of the simulation measurement theta K splitting into two parts, theta K1 and theta K2, that are two separable POVMs. So this has a line of work. So it was first solved in the side information case by Wild in 2012, and then that was in the asymptotic setting. And then it was again solved. It was solved in a kind of different way in the one-shot setting, because the Wild and the Winters POVMs cannot be simulated in the one-shot because they needed the joint typical POVMs. So so Anshu, Jain, and Varsi did it in 2019 with a one-shot setting. So they did a different way of approach of doing this quantum measurement compression in the one-shot. But it turns out this cannot be generalized again to the distributed setting. In 2022, Pradhan, Atif Haidari and Pradhan, they solved the asymptotic case in the distributed setting. But again, that uses time sharing and cannot be used in the one shot. So I wanted to come up with one thing that works for everything out there, whether it is distributed or single shot, one shot, or with side information, all of that scenarios in just one POVM with a simple proof. And that's kind of what I've been able to do. So so these the work of Atif Haidar and Pradhan did it in the asymptotic, but it doesn't work in the one shot because of time sharing. So I was able to do it in the one shot, and that works in all scenarios. Very simple proofs, and that's the upshot. So how do I do it? So let me just kind of briefly tell you how I do it. So if you look at the so you need an alternate POVM that kind of simulates the original POVM. So if you look at the POVM, the POVM looks something like this. So it's all kind of started from Winter's work. This was in 2004. So this was the POVM that he considered. So at the so you have the post measurement state here, actually, in some sense. And then because you can't build a POVM out of this, you will have to coat them with some projectors. and then you kind of have to analyze it. So that's what it is. So this is the post measurement state coated with projectors to ensure that you get a POVM. So that's the broad. I'm getting into some details here, but if you looked at this post compression problem, you'll kind of understand. And so what is happening is that they want a collection of POVMs. If you just put these, it doesn't form a POVM. So you coat them with projectors, and then you kind of normalize it so that you can make a POVM out of it. And you have a bunch of projectors. There is a projector for the, there is a typical projector for the pi for the rho. There is a cutoff projector for pi hat, and then there's a bunch of projectors that kind of make it. But then because now this uses typicality, you can't push it in the one shot, and there are a lot of constraints, and analysis becomes complicated because they don't commute and all of that. So the way I worked on this is, well, I'm going to just do a very simple analysis. So this is the post measurement state, right? So it's I mean, if you take this is your post measurement state. So let's take, in the asymptotic, where does this go to? This goes to essentially this, which is what at the heart of the POVM that they've all constructed. The problem you can't live with this is because it doesn't add up to a identity. So it needs to be normalized. So that's why you need all these cutoff projectors, and then you add some fluff, and you kind of make it a POVM. I'll do something very simple. I'm going to just normalize this system. So I'm going to take this so if I just take this center core of the POVM, just normalize it, and then work with it. The question is, will it work? It will work, but the problem is the analysis gets complicated because at the denominators you have these random objects, and you don't know how to analyze it. So it turns out it's not difficult. So I just went ahead a little bit, and then you can actually show that when you actually analyze it, you don't need to worry about it. It turns out that the normalization factors will actually get killed in the analysis. When you do the analysis, it turns out one of the rate bounds tells you that the normalization factors indeed has to go to rho, has to actually tend to rho. So if you actually appeal to that, so instead of operating on the original state rho, if you operate on this state itself, you can actually show that the normalization terms get killed, and you can just analyze the entire thing out very simply. And so you don't have to do any work, and it kind of, in some sense, self-destructs. And the analysis goes through, and you can do this. You can use this POVM, the simplest POVM, for every problem out there. And only thing is, you should not you should not operate it on the original system, but you should operate it on the proxy state, which is actually this. And the proxy state will indeed is guaranteed to converge to the original state, because that's one of your rate bounds. So that's as simple as it. And it turns out that one of the rate bounds guarantees this, and you can do all of the analysis in the distributed setting, in the point-to-point setting, in this in the one with the side information. In every setting, you can just use the same likelihood POVM and analyze the whole thing, and you will be able to get one-shot rates. You will be able to recover all of the known coding theorems out there with covering. So that's kind of the broad message. So no time sharing, no typicality projectors, no projectors at all, but very simple analysis, and can be used for any problem out there in the covering scenario. That's essentially the talk. You can extend this to purity distillation, quantum reverse Shannon theorems. All of that pretty much is very simple work, and recovers everything in one shot, in universal technique for one shot, asymptotic and everything. So that's essentially work. You can universal proof techniques for all quantum classical covering. I'm kind of done, and if you have any questions, please feel free to ask.
So you had some slide where you had the scheme of the simulation. Can you show that again?
Yeah.
So you simulate the
So
my question is, like, you replace the POVM in the first place, and then you basically only communicate classical data, or what, or did you simulate on the second, like the receiver side?
So the idea is this. So this is your so this is the original POVM acting on the state. So when you make this POVM, when you operate this POVM on the state, this is the outcome that you get, right? So the question is, how much information does this contain about the state? So if I can simulate this post measurement correlation between the classical part and the quantum part using any other mechanism, so then I've essentially simulated the POVM. That's the idea. Okay, so I'm going to do it in a different way. So the way I do it is I'm going to take an alternate POVM that has fewer outcomes. Okay, so that's only going to give me, say, a fewer number of outcomes. And I'm going to make that measurement. And that fewer outcomes is going to be stochastically processed with some common random bits. If this process can actually simulate the same post-measurement state as the original POVM, then all that I needed to send to the decoder was this W.
Yeah, which is the classical. So stochastic processing is completely classical.
If this has lesser number of bits, then I don't need it to send all this Y to simulate the classical outcome. So the information content is only the cardinality of this and not the cardinality of this, or the entropy of that. That's the idea. Now, so you need this extra bits of randomness. So this extra bits of randomness will help you mix these different possible outcomes to in the right fashion. So that's the formulation here. So you're trying to, so this is your post measurement state from the original POVM. You do a bunch of different POVMs, mix the outcomes so that you can get to this. So, and then the question is, how many outcomes do these give? That's the information rate. That's the information you're getting from the measurement.
Yep.
And so I lift this up in the distributed scenario. But in the problem in the distributed scenario, you can't do the proofs that you did in the previous case because there are lots of issues. And even the simulation POVMs are involved because they have the typicality projectors. They don't go into the one-shot setting. And the question is, can you do it in a one-shot setting? So you can, in some sense, and it's actually simpler than the previous ones.
Yeah, and to this distributed system to work, it's like for this to work without like having shared randomness between all three parties. It's essential that it's separable, isn't it?
You don't need randomness between three parties. You only need randomness between the senders and the decoder.
Yeah, but you're only simulating separable POVMs where the correlation
you are only able to separate. Yes, because
classical.
You need
the, and for this, it's fundamental. Like for this to work, it's fundamental that they're separable because you don't have shared randomness with all three parties. Or what?
Separable only in the POVM.
Yeah.
Not the states are entangled.
Yeah.
So the in other words, what is separable POVM saying is that I should be able to do separate measurements and mix the outcomes so that I can simulate the original POV. That's all pretty much to it. Yes, but if it's not a separable POVM, it's not possible to do it in a distributed fashion.
Yeah.
Yeah.
Okay. Do we have any more questions now?
Not a question as much as a historical comment. So I wouldn't like it to be forgotten that the origin of this question wasn't my work. So I worked on this because of an earlier paper by Serge Massart and Sandro Popescu.
Yeah.
They had seen this in a setting that was more like rate distortion, like a quantum rate distortion setting. And then I worked with Massart on generalizing it, and that was the first time this actual rate, the communication rate as a mutual information came out. And only after thinking about this for more than a year continuously and publishing those and having seen those previous papers, that version that you showed of the measurement compression came out. So this didn't come out of nowhere. This had a sort of a much more innocent looking origin actually, and one that is also much easier to understand in many ways. But yeah, anyway.
Yeah. I actually recognize that. So in the first slide, I had something like your work followed series of works. I think Popescu, Massar, there was a Popescu work, and then there was a work by Massar and you, and then there was your work. Yeah, I think this, yeah, I think this question was posed a long time ago. Even in the 60s or 70s, there was a question about how do you quantify the amount of information content. Grunewald, or one of them, had actually formulated this.
Like, I think you're right. I mean, the sort of the philosophical question has a long history, but the model of that paper is really closest to Massar and Popescu. What was really interesting that it was I knew what to do it because I had seen already this link between channel simulation and rate distortion in other settings. So it was kind of, after a bit of thinking, it was clear what to do, and then after a bit more thinking, eventually this came out.
And this was prior to the work by Cuff in the classical scenario. If I am right, I don't think Cuff has cited your work in that. I mean, possibly the connection between quantum and classical was not there. Yeah. Thank you.
Okay, let's thank him again.